Okay, good morning, everyone. Please turn your camera on. Okay, please turn your camera on. It will be very helpful for me. Okay, how did the homework go? You guys have any questions? How did you do? Okay, and oh, all right. So we're gonna do number 2, part K, and we will do number 2, part O and M. Very good. So let us get started. I start with K. All right. So we have to find the integral of sine of 2t cosine square 2t to dt. Okay, so of course I will need your input. So the first thing, and whenever I see cosine square, we're going to get into the habit of writing it as cosine 2t to the power 2, especially when we are integrating, because it helps me to see the picture. All right, and now back to you. Do you see an inside function whose derivative is part of the integral? Anyone?
Cosine 2t.
Cosine 2t, because if we look carefully at cosine 2t, its derivative is the sine. Now up to a constant, but we know from yesterday the constant is not really a big issue. So we're going to put u to be the cosine of 2t. Then immediately du dt is the derivative of cosine, it's minus sine times the derivative of the inside, never forget the chain rule, dt. Sorry. Okay, so this tells me that the du is minus 2 sine 2t dt. And now I stop here, I go back to my integral and try to connect the dot. All right, so let's see what my integral becomes. It's the integral of, okay, the cosine 2t square, this is the u square, no problem about that, times sine 2t dt. Now if I look, now I start looking at the du. So I realize I don't quite have, the du is not quite sine 2t dt, but I can figure it out from here. So if I divide by minus 2, or I multiply by minus a half, I will have minus a half du is the sine 2t dt. So now I will have u squared times minus a half du. So this piece right there, this piece here is the minus a half du. With this in mind, I am basically done. Now I have a very simple integral in u. Minus a half is a constant. I take it out. So this will leave me with minus a half. Antiderivative of u squared is 1 over 3 u to the power 3 plus a constant c. So finally, I will have minus 1 over 6. The u, I go back and substitute in terms of x. It was the cosine of 2t plus my constant c. Okay. And now, since this is a simple one, we can check. Okay, Checking means I have to find the derivative of what I got and make sure I get what's inside the integral, what we call the integral. So let us check this. So we're gonna take the derivative and see if we did it right. Equal. All right, let's differentiate. -1/6 is a constant. Derivative of cosine 2t to the power 3. So let us remember. Here I have an inside function. That's my inside. And my outside is the cubing function. So the derivative is the derivative of the outside, which is 3 times square, evaluated at the inside, times the derivative of the inside. So now I will have -1/6 times 3 will leave me with -1/2. The cosine of 2t times the derivative of cosine 2t. Again, that's inside, outside, chain rule. It's the derivative of the cosine times the derivative of the inside, which is 2. And now we're done. 2 cancel out, minus and minus give me a plus, so I will end up with sine 2t cosine 2t squared. So I am doing fine. All right. So we won't check every time, but at the beginning, we have always to remember what we are doing. We're finding a function whose derivative is the integrand. The derivative is what's inside the integral. Okay. All right. So let's move on to the other one. We have two more to go. So part O. What is it about? O is, okay. Integral of 1/x ln of x dx. Again, this is it's a substitution, and we have to look at the integral and decide what shall we do. Okay, I'm gonna pick one of you, and I want to see what they done. Tristan, are you with me? Tristan, are you with me? Nope. Please put your camera on. Please put your camera on. Okay, let's pick another student, see what they get. Stephen Smith. Participation is part of your grade.
I can do it.
Go ahead.
I got ln of x plus c.
I don't want the answer. I want the steps. That's what I care about. And then the answer, we worry about it. How did you think about it?
Okay, so for my u was ln of x.
Ln of x, because did you see what gave you the hint? Go ahead.
It seemed like, it's kind of hard to explain, but it's almost like the whole thing was ln of x because it's 1/x. So I knew how to handle that, but the one ln of x in the denominator, I didn't really know what to do with. So
I mean, that's a good reason. He didn't know what to do with the ln of x. He put u to be ln. That's one good reason for it. Another good reason for it, if u is ln, its derivative is 1/x. So basically, I have the derivative of ln also as part of the integral in this particular problem. Okay, so I'll follow you. So you put u to be the ln of x. So the du become 1/x dx. Look, and then what did you get? Keep going. So your integral become what as an integral in u? 1/x dx. That's my du. And I will have 1/u du. Now, it's an easy integral in u. So that will give me ln of u plus c. Now I go back to my original variable x, ln of x plus c. End of the problem. Okay. All right. So now we look at the questions. Before I move on, please ask questions if something is not clear.
I have a question.
Yes, please go ahead.
So all you would do in the beginning is just split the fraction. Is that what you did?
Which step? This step?
Yes.
Yeah, I just trying to rewrite it so you can see the derivative of ln inside the integral. Okay, so that's rewriting it. You know what I mean, rewriting?
Yes.
Yeah, because 1 over x ln is basically, I mean, if it's the fraction, if you have 1 over a times b, it's 1 over a times 1 over b. So multiplying fraction is multiplying the numerator over product of the denominator, which is a times b. And that's basically what I'm doing here. It's 1 over x times ln, and I rewrote it as 1 over x times 1 over ln. But the reason I rewrote it is I want you to see that this piece is the derivative of ln. So you can start connecting dots. All right? Does this answer your question or not yet?
Yes, it does. Thank you very much.
Okay, so let us look at M. M, what is it about? Okay. M, the integral of cosine 2t over 1 plus 6 sine 2t dt. Okay. Who would like to share with us what they did?
I can do it.
Go ahead. Go for it.
I said u equals 6 sine of 2t.
Okay. We're going to set u equal. Why did you pick that?
Because the derivative of sine is going to be cosine, and then the constant doesn't really matter.
Yeah, that's a good, definitely that's the idea. So your du dt gives you what? Let me know. That's the derivative.
6 cosine of 2t times 2.
Times 2. So my du will be 12 cosine 2t. Okay, very good. So let us substitute verbatim, and you have to help me with what you got, okay? So what did we get when we substituted?
1 over 1 plus u.
So 1, okay, and here what happened in the numerator?
And then you need 1/12 to.
Right, because the cosine 2t dt is not quite the du. Okay, so I need to isolate this piece to get the numerator. So I had to divide by 12 here. And this would give me the cosine 2t dt. So this is going to be 1 times 1 over 12 du. Very good. So this will be equal to. Now the 1 over 12 can go du. Very good. Now, after that.
It's 1/12 times the natural log of 1 plus u.
Why can you say immediately the natural log? It's not u. Okay, if you had 1 over u du, I agree with you, it's immediately the natural log. But you have 1 plus u. Your answer is correct, but it's not immediately.
I don't know.
Yeah, so in case you do that, okay, that's why I'm glad you did it this way. I will need another substitution. Okay, because I don't have u here. If I had 1 over u du, you're fine, that's the ln, but I don't. So I would have needed another substitution, like t equal 1 plus u. I do that, so we can do it basically as many substitution as we want, which is okay. dt would be the du. And then this would become 1 over 12 integral of 1 over t dt. Now, this is exactly the ln. Now I am safe. This would be the ln of t plus c. And now I have to, sorry, what's happening here?
I have a question.
I'm listening. Very good.
I did the +1. I did that in the beginning, so I did the
Exactly.
U.
I want to definitely. I want to mention that absolutely. But now I have to keep working with with what your classmate said, because it's actually correct. But I want to point out this issue here, that you cannot write ln. Ln it should be 1 over u du. So if you have 1 plus u, fine. You need another substitution to make sure you're getting it right. So now I proceed 1 over 12 ln of, now I have to go back. T is 1 plus u, but u is the 6 sine 2t plus c. Okay, absolutely correct. And then I will do it a second way, the way your your other classmate is telling me. So she definitely picked u to be 6 sine 2t because she saw the derivative in the top, which makes a lot of sense. Then the du dt, we proceeded. We did every substitution correct. Then when we reach here, that's not immediately the ln because I don't have u here. So I said, okay, not a big deal. I put t to be my 1 plus u. So I did another substitution. Of course, I cannot call u. I have to make another variable, which is all right. No problem with that. This will give me 1 over t dt. Now I am safe. That's the ln. And now I go back to my original value. Okay. Now, another way to do this problem, to avoid doing two substitution, another way to do it is from the beginning. So another way, so I will pick it up on another piece of paper. So another way is from the beginning to put 1 plus the sum. And this would save us a little bit of work. So I will do it. Or, it's in or because we can do this. I can pick my u to be the whole denominator, which will make it slightly easier for us. I pick it to be the whole denominator. That's my u. My du would be, derivative of 1 is 0, so it's not really affecting anything. It's still 12 cosine 2t dt. And now we substitute. I will have the denominator now is my u. Now the numerator, cosine 2t dt. This become, I need to isolate the cosine 2t, so I divide by 12, so 1 over 12 du. So exactly like before, but I took the whole denominator to be my u. So this is going to give me 1 over 12 du. Now I am safe. So 1 over 12, I can take it out. I will have 1 over u du. It means 1 over 12 ln of u plus c. Of course, we're going to get the same thing. 1 over 12 ln of 1 plus 6 sine 2t plus c. End of the problem. Okay, so you can do it two ways, absolutely. The second way is a little bit shorter. So we pick q to be the whole denominator. We are safe because the derivative of 1, it's 0. So the derivative of the denominator is right there in the numerator. And substitution is the way to go. Any other questions before we proceed? Okay, so today we're getting hopefully to the end of the review. So today we're going to review the definite integral and then the fundamental theorem of calculus, and then we start basically our course. So review the definite integral. So review 3, you want to call it definite integral. Okay. So to talk about definite integral, I first have to talk about Riemann sum. So as I repeat, this is review, so I will do it faster than we've done it in 163. So suppose you have a function f. So I have a function f of x. And this function is take bunch of positive value and negative value. So this is my function. So this is my function f. And this is my interval a and my interval b. And b. Now I will define first what we mean by left Riemann sum. Riemann sum. Then I define what we call the right Riemann sum. So what's the left Riemann sum? We take the interval AB and we divide it into n equal pieces. Okay, so we take interval AB and we divide it. So we divide AB into n equal subintervals. So we divide it. Divided, and so on and so forth. Okay, so we divide into n equal subinterval. And I'm going to label those. So I'm going to call this x0. I will call this first subdivision x1, x2, x3, and so on and so forth. So since it's n pieces, this is my xn, and this is my xn minus 1, the one before it. And we call delta x the length of every piece. So from here to here, that's the delta x. Delta x. Now delta x is what? My whole interval, the length from here to here, it's b minus a. I divide it into n pieces, so delta x is b minus a divided by n. Now, what's the left Riemann sum? We take this interval, we split it, and we take the following sum. We take the value of the function, so you add my subinterval. The left end point are a, x1, x2. So we take the value of the function at the left end point times the delta x plus. So this is the value of the function at x0. We take this and we multiply it by the delta x. That's my delta x. That's the little bit. I add to it the value of the function at x1 times the delta x. So I evaluate the function at x1 multiplied by delta x. And I keep going. F of x2 times delta x. And I keep going, and I keep going, and I do that for every piece. So f, the last one would be f of x minus 1 times delta x. So this is the left Riemann sum. So we have actually a function and we take this sum. And in sigma notation, this would become sigma f of xi. So this is what vary in the sum, 0, 1, 2, 3, times the delta x, where my I, since it's a left sum, goes from 0 to n minus 1. So that's what we call the left Riemann sum. So it's the value of the function times the delta x plus the value of the function at x1 times delta x, and so on and so forth. And we can talk about something called the right Riemann sum. The right Riemann sum, it's the same as the left, but instead of starting to take the value at x0 times delta x, we take the value at x1 times delta x. So there will be a shift. So I take f of x1 times delta x plus f of x2 times delta x plus, and so on and so forth. f of xn times delta x. So in sigma notation, this would become, I'm adding quantities that have the form, the value of the function at a point times the little bit of delta x. Okay. So that's left and right Riemann sum. Crucial. Now, the idea is when n takes large value, it means I subdivide this interval. Suppose I subdivide it into 10 pieces. I compute this sum and I compute this sum. Then I subdivide it into 20 pieces. I compute this sum, I compute this sum. Then what we realize that when we take a lot of subdivision, those two values actually will become very close to one another. So when n is large, left Riemann sum is almost equal to the large Riemann sum, to the right Riemann sum. So that's what happened when n is very large. Now, what is the definite integral? Of course, we will have an example. We're going to compute the sum. All right, so now what's the definition of the definite integral? Definite integral. Can I move on?
Yeah.
Everybody?
Yes.
Very good.
Yeah.
What is the definite integral? Definite integral, that's the definition. Crucial. Definite integral. So, suppose I have the function f of x. So let f be defined on an interval ab. Then the definite integral of f denoted by, that's the notation. Most of us, of course, know the notation. From a to b, f of x dx, that's the notation, is defined by. So that's the definition. That's what the definite integral means. It's the following. The definite integral is what happened to those Riemann sum when n is very large. It means when the number of subdivision becomes larger and larger, what happened to the value of those sums? That's what the definite integral. So mathematically we write, it's the limit as n tends to infinity of the Riemann sum. Whether you take the right, you take the left, honestly, it doesn't really matter because both of them will have the same value when n is very large. So let me take, for example, the right one. The right is f of xi delta x. In the right, we start from 1 to n. And whether you take, as I said, left or right, it doesn't actually matter. So I will take both of them, which is the same as the limit of the sum of the f of xi delta x, I equals 0 to n minus 1. So that's the definition of the definite integral. So what the definite integral is, we take those Riemann sum, and then we ask ourselves, when we take more and more subdivision, what do they get close to? And that's what they get close to is exactly what we call the definite integral. Now, the notation, where is the notation coming from? The notation for definite integral, so this notation is due to, I'm listening.
The n over the right sum, should that be n minus 1 or is it just n?
For the right sum, n, because when I do the right sum, let me go back to the picture. I start at x1, okay? So I take this, I divide it, and I look at the right endpoint. Those are the right endpoint. Okay, and then I take the value at the right endpoint times the delta x. and I add to it the value of the function at the right endpoint times the delta x. Now, what's the last right endpoint? Is this one. But this one is xn. Okay? In the left one, the last left point is the one before it. So we stop at xn minus 1. For the right one, we stop right there.
Yes, I understand
Make
now.
sense?
Thank you.
Okay. Very good. Now, what is the notation? First, the notation is due to a mathematician and philosopher called Leibniz. He came up with this notation. And really, what really triggered this notation? What triggered his notation is the following. First, this sign, as probably you guys know from calculus 1, is the letter S. S stands for sum. Is the letter S, which is elongated. That's what this is. And why it is S? Because Leibniz is trying to remind us that the definite integral is a sum. So this is really reflect the idea that we are adding. What we are adding. The integral, what's he right here, reflect what we're adding. We're adding quantities of the form f of xi times delta x. And here the delta x changes. So this delta x is b minus a over n, depending on the number of subdivisions. So I repeat, the notation is totally inspired by what it reflects. It's we're adding quantities of the form f of xi delta x. That's really where the notation coming from. Now a and b tells me which interval I need to subdivide into pieces to be able to get this sum. So a and b are called the limit of integration. A is called, so this is a and b. A is called the lower limit. And b is called the upper limit. Okay. And the notation, as I said, is really try to reflect what we are doing. We're adding those quantities when n, by taking n larger and larger and larger. Now we're going to do an interpretation of the definite integral, and then we're going to compute at least one of those sums. So let us interpret the definite integral. Interpretation. Now I'm going to ask you, what's the interpretation of the definite integral? Anybody remember? So geometric interpretation or graphical interpretation.
Is it net area?
It's the net
Is that what you're
area.
looking for?
Absolutely,
Okay.
it's the net area, at least for now. And then the goal of the first part of the course is to give us a lot of interpretation of the integral. I mean, how it's used. But for now, I'm going to divide my problem into two pieces. So case one, because it's crucial, suppose the function is positive on the interval AB. Only positive, okay? It's crucial. Then what does the definite integral represent? Remember, the definite integral, to understand it, you have to know what it is. It is those sums when n is large. So to understand what this means, we have to understand what the Riemann sum are. So if we understand what those represent, then we can actually understand what the definite integral is. So if the function is positive, I'm going to draw first two pictures, one for the Riemann sum, and then one for when n is large. So if f is positive, so that's here. That's A and B. And as we know, when I start taking those Riemann sums, I start dividing, and of course I'm not gonna, whether I take the left or the right, it doesn't really matter. So if I take the Riemann sum, I'm gonna get the following. The value at A, so let me concentrate on actually I want the right one. So the value here at x1 times delta x. No, the value at x1, as you know, is gonna give me the height from here to here. Delta x is this little bit. So f of x1 times delta x, this is nothing more than the area. of this rectangle. Then I'm going to add to it f of x2 times delta x, right there, which is going to give me the area of this rectangle, and so on and so forth. I keep writing this piece. So the Riemann sum in this case, so plus etc., f of xn times delta x. So the Riemann sum is the sum of the area under the rectangle. Sum of the area of the rectangle. So that's the interpretation of the Riemann sum. Now, what is the definite integral? When n goes to infinity, it means when n means n is very large, is when I take more and more subdivision. I take more subdivision and more subdivision and more subdivision, and then what this Riemann sum start giving me. So when I take more and more subdivision, the integral in this case is what happened to the sum of the area of this rectangle when n is large. So this is going to become the area, the actual area under the graph. So it's this area. Okay, because by definition, that's really what it is. By definition, this is nothing more than the sum of the area of the rectangle. But when I take a lot of rectangle, I actually fill up this region, totally fill it up, and that's going to give me the area under the graph. So as long as f of x is positive, this area, the definite integral, represents this area. So I have a graph, I want to compute this area. Basically, it's nothing more than those sums when n is large. So the last thing is what happens when f takes positive and negative value, how will be affected. Part 2 is f takes positive and negative value. F takes positive and negative. Okay, the first thing we will study is the Riemann sum, and then what happened when the Riemann sums, when the number of subdivision become very large, because the integral is a bunch of Riemann sum. To understand it, I have to understand the Riemann sum first. So again, I start by trying to analyze the Riemann sums, and then we see what happens when n is large. So again, let me take, this is my function, but this time I want to take it taking positive and negative value. So this is my A, and this is my B. And I'm going to divide it, but this time I will take few subdivisions, not a lot, so I can explain what's going on. And I'm going to take the right sum, because it doesn't really matter at the end. So I'm going to call this x3, x4, x5, x6, and x7. So I will write the Riemann sum and analyze it. So the right Riemann sum equal to. Okay. So if I take the right one, so I start at x1 times the delta x plus f of x2 times the delta x, f of x3 times the delta x, f of x4 times the delta x, plus f at x5, delta x, f at x6, delta x, plus f of x7. So I took only 7, so I can explain it. All right, so let us analyze every little piece. What does f of x1 times delta x represent in the picture? F of x1 is from here till we hit the curve. That's f of x1. When I multiply it by delta x, I'm going to get this area. Plus f of x2 is the height from here to here. And then when I'm going to multiply it, I'm going to get that area. F of x3. This is f of x3 from here to here. So this point is, as we know, x3, f of x3. And this is the delta x. I'm going to get that. F of x4 is, in this particular situation, 0. It's not a big deal. Now, so f of x1 is, if I call this region R1, it's the area of that. I call this R2, it's the area. I call this R3 is the area. And this is the area is 0. So this is area of R1 plus area of R2 plus the area of R3 plus whatever, it's a 0. Now, the question is here. That's really the question. So let me take f of x5. This is x5. F of x5 is negative. It's negative number. And this is the delta x. So the question is, f of x5 times delta x represent what in terms of the picture? Remember, f of x5 is negative. Means if I evaluate the function at x5, I'm going to get a negative number. -2, -3, -4. I really don't know. So when I take it and I multiply it by the delta x, what do you think I should get?
Negative number.
Negative number.
I'm going to get negative number. Okay, so it's not an area anymore because a negative number. But we're going to relate it to the idea of the area. It's going to be equal to what? Let us say, for the sake of argument, of course, because I don't know what f is. So let us say the value of the function at x5 is, let us add any number, -2, for example. You don't have to write, I'm just giving you a number. So I'm taking -2 times delta x. What am I taking in terms of this area? If I factor out the minus, because there is a minus, I will have 2 times delta x. But what does 2 times delta x is? So it means the length here, the length now, not the value, the length is 2. And this is delta x. So 2 times delta x represent the area of this rectangle, the 2 times delta x. So f of x5 times delta x is going to represent minus the area of this rectangle. Okay, so if I call this R5, R5, so this would represent, this would be minus the area of R5, not plus, minus the area of R5. The same for f of x6, because f is negative here. So when the function takes a negative value, f of x5 times delta x represent minus the area of this, not plus anymore. This is the same thing here. So this is minus the area of R6, and this is minus the area of R7. Because as you realize, I'm analyzing the Riemann sum because that's what the definite integral is about. So what does the Riemann sum represent? Now let us sum this up. It's the area of this plus the area minus this area minus this area minus this area. So it's going to be area of the rectangle above the x-axis. But here I'm going to take away the sum of the area below the x-axis. So I'm going to take away the sum of the area below the x-axis. The x-axis. So that's what the Riemann sum actually represents. So the Riemann sum represents the area, sum of the area of the rectangle above minus the sum of the area of that. That's what the Riemann sum represents. So now that we understand what the Riemann sum is, now I can understand what the definite integral, because what the definite integral is, I take more and more subdivision and see what happens. So now what I'm going to take more and more subdivision, the definite integral is going to be, so I take another piece of paper. Okay, so now the definite integral is, so again, I have the same region. So when n is large, or when n goes to infinity, means when I take a lot of subdivision, what happens is the following. What's the definite integral? I draw the same curve. Exactly. That's my A. That's my B. And the definite integral become equal to. So when I start taking n very large, then I'm going to get the area of the region above, because that's what the Riemann sum actually tells me. When you take n very large, you're going to take, so it's the area of the region above the x-axis I have to take away from it area of region below. And that's what your classmate called the net area. And some book called the signed area, signed, because we're taking the sign into consideration. So the integral, when the function takes positive and negative, the integral is not the area anymore. It's the area of the region above. You take away from it the area of the region below. So that's really what the definite integral represents, because that's what the Riemann sum are. That's because what the Riemann sum are, and that's what the definite integral is for us. All right, this is a small example. So to put this in perspective. So let us say I take the following function. Let f of x equal, whatever. No. Suppose I take the following function. So example number 1. So let f of x be, let us say x squared minus x. And the question is, estimate definite integral from 0 to 2 of x squared minus x dx, estimated, that's a definite integral. The definite integral is the Riemann sum when n is large. But of course, taking n very large is hard for us, so we're going to estimate it using right Riemann sum with, okay, let me take 8 subdivisions. Okay. So before we do the estimate, let's see the picture of what's really happening, and then we do the estimate. So let's see what the pictures are. So here, what is my function? First, my interval. My interval is 0, 2. That's my interval. My function is x squared minus x. So if I draw the function x squared minus x, that's a parabola. That's a parabola going up. At 0, I am at 0. So if you guys draw it, you get something like that. Okay, that's really the graph. And this should be x squared minus x equal to 0. This should be a 1. So that's really the graph of my function. So it's negative and it is positive. Now we're going to divide it into 8 subdivisions. So my delta x is, the length of it. So that's the 0, 2 divided by 8, which is going to give me 1 over 4. Okay, so that's my delta x. So I have to divide it into a lot of pieces. So this is 0, 1, 2, 4, 1, 2, 3, 4. These are my subdivisions. And this is 1/4, and this is a half, 3/4, 1, 5/4, 6/4, 7/4, and now what's the Riemann sum? Let us remember what we do. So we're going to take the value here times the delta x, the value here times delta x, and those are going to be negative numbers. So when I take the value at x4 times delta x, I'm going to get minus this area. Then I'm going to get minus that area. Then minus that area.
I have a question.
I'm listening.
Didn't you say we were going to use the right Riemann sum? So wouldn't we start from the right side?
Yeah, x, this one. That's the first. When I say right Riemann sum, it means on every interval, you take f, the value of the function at the right endpoint of the interval. It means here. What are the right endpoint? This one, this one, this, this, and that. What's confusing you? Ask your question.
Oh
again.
no, I just thought you had to start from the right side, like from
that's-
the right side of the graph.
That's the right. No. It means on every interval, you start from the right endpoint.
Oh, okay.
Not,
All right, I was confused.
that's the right. It's not the left. It's on every interval, you take the value at the right endpoint of that interval. Then you move the value at the right interval. Are you still confused?
No,
you-
okay, I think I understand now.
That's okay. That's why I did the problem. Very well. And then I'm going to take at x4. At this stage, the value at x4 times delta x will pick up the actual area. The actual area now. The actual area. And now it's also going to pick up the actual area. So here it's minus the areas. These are the Riemann sum. And this is the path of the area. So what is the Riemann sum? Let's write this down. So the Riemann sum. And that's an estimate of the integral, not the actual value, because I'm only taking its subdivision. So it's the value of the function at 1/4 times the delta x, which is 1/4, plus the value at 1/2 times delta x, the value at 3/4 times delta x, and we keep going. The value at 1 times delta x, then the value at 5/4 times the delta x, at 6/4 delta x is tedious. So that's why I will give you the answers. We're not going to do that. Plus the value at 2 times delta x. Okay. Now, the value at 1/4, it means, so I will just make sure you understand this piece. It means my function is x squared minus x. So f at 1/4 is going to be, we evaluate the function at 1/4, so we get 1/4 squared minus 1/4 times the delta x, which is 1/4. That's really what we're going to get. So here I will get 1/16 minus 1/4. This is definitely a negative number. That's definitely a negative number. So when I multiply it by delta x, I'm going to get minus this little area. So now I compute this, and we do all the math, or we use any, and I will get that much. And this is my estimate. It means my integral, x squared from 0 to 2, so that's an estimate, is almost equal to 0.937. And the more subdivision I get, a better estimate I will end up with. Okay.
I have a quick question.
Okay, I'm listening.
The delta x, that became 1/4 y.
The delta x is 1/4.
Oh, why is that?
Oh yeah, because I have the integral from 0 to 2. Okay? So
Okay.
this is 0, this is 2. Using 8 subdivision, it means I take the interval from 0 to 2 and I split it into 8 pieces, equal pieces. So I have this interval, length of 2. I divide it into 8 pieces. What's going to be the length of every piece if I do that? So the length of every piece is, I have 2, divided into 8, it's 1/4.
Okay. All right. Thank
So,
you.
and the delta x is from here to here. That's my delta x. That's my delta, this little bit. This is my delta x. This is my delta x. Is this making better sense?
Yeah, it makes a lot more. Okay. I was just wondering because I saw that you did the math to find 1/4 to divide the subsection, but I didn't realize that you pulled that directly into delta x. But I get it now. I'm okay. Thank you.
All right. So that's really what my delta x is. And when the number of subdivision becomes large, the delta x becomes smaller. And that's crucial. The more subdivision, the smaller the delta x. And that's really what we want. We want eventually to get the net area. So we want to cover it with more and more rectangle. So that's my good estimate. Now, build up a feeling for the notation. So my second question is, and then I think I have to quit. So my second question is, it's the same problem. My question is express the integral from 0 to 2 of x squared minus x dx as a limit of Riemann sum. What do I mean by this question? And let me write Riemann sum. Okay. So what do I mean by express this integral as a limit of right Riemann sum? So what I mean by that is the following. So it's the abstract idea. It's equal to what? Basically, when I say express as a limit, it's the definite integral is the sum of Riemann sum. So the sum of. So my function here is x squared minus x. And the idea is that we're going to take it f of x squared between 0 and 2 and divide it into n subinterval. So the summation of times delta x. The value of the function at xi, so that's really what I mean, minus xi, I equal 1 to n, that's the right Riemann sum, and we take the limit of that as n tends to infinity. So that's what I mean by expressed as a right Riemann sum. Now the delta x actually change with the number of subdivision. So another way you can write it is the same thing, that's the value of the function, and the delta x is basically b minus a over n. That's really what your delta x is about. So when I tell you express as a limit of Riemann sum, it means I want to start building a feeling for this notation. It means this integral is the limit as n goes to infinity of those sums. Okay, that's just a little bit abstraction, but because we actually need it very soon, right? Okay, I stop right there. And I will put your homework for tomorrow, which is basically computing two problems where you have to compute left and right Riemann sum. Right. Any question before we let go?
Will the homework be on my lab today?
No, not yet. The my lab will start when actually I start the course. So far, I'm reviewing.
Okay.
All right. So for me, all this is a review, but it's a necessary review. I will not plunge you into the course without doing this review. Okay. I still have tomorrow, and then after that, we start the course. All right. And I really appreciate it if you guys turn your camera on. It's really helpful for me. So please do it tomorrow. Right?
Professor?
Yes. Sure. I'm here.
Is the review one that you assigned on the first day that
Yeah.
you're talking about, that is due tonight?
The review is done because we've the review one, I mean, it was, you should have done it for today. You should have done it for today. So today, right now, after I finish with you, I'm going to put another worksheet, which would be the second review.
Okay.
Right? And which cover Riemann sum. And then tomorrow I will have, I will finish the review and you will have more problems. So the worksheet I'm going to put today with the explanation of which problems from the worksheet you should do, that will be for tomorrow.
Okay.
Right?
Also,
yes.
So I missed the first class, so because I was late in getting registered, so I'm kind of confused about like how we're doing and turning in our homework, and I've been like
this week you're not turning in anything. Okay, this week.
Okay.
All right.
Okay.
So you're safe this week. Starting Monday, you will have to turn it in using my lab. Are you with me?
Okay, yeah. So the reviews then that you guys were just talking about would be just practice for us.
That's practice. That's practice. And it's crucial practice. You're going to have a quiz on it on Friday. So your quiz on Friday will be
Okay.
The
Okay.
quiz on Friday will be based verbatim on the review I am doing, period. Okay, but turning them in, we're gonna turn them in using my lab. You've used it last semester, I hope, or whatever. It's not. Yeah. Then this will start on Monday. So this will give everybody time to purchase it and stuff like that.
Yeah, so we have to purchase we have to purchase an e-textbook online and with an access code.
I think, yeah, the access code, if I understand very well, if you purchase the access code, the book will be part of it, but it will be online.
Okay, so
And
because for one of my classes, it gives me the option to, it says like register, and then it gives me the option to purchase it for $95 rather than $65. Would the $95 one be with the actual text and the access code?
You have to read the details. I actually don't
Okay,
know.
so you wouldn't be able to tell me that.
I don't know unless I read the details.
Okay.
My advice
That's
to you
all right.
guys, yeah, my advice to you, if you guys want to take Calculus 3, there is an access code that works for 24 months.
That's what I was going to say.
Yeah, go ahead. I think that's better for you because most of you are going to take Calculus 3, I hope, because, you know, if you're taking Calculus 2, you're going to take Calculus 3. So last semester, I advised my student to purchase the access code for 24 months. That's my advice for them last semester. I don't know what they did because, you know, they would have saved money now and they will save money for Calculus 3. For those who don't have the access code, purchase the one that will give you access code for a longer period of time, not only for one semester. Okay, for 24 months. Now, two things. First, you need to Calculus 3. And if by any mistake you didn't make it in Calculus 2, then you will still have it when you retake it. So so instead of buying it only for this semester, buy it for, you know, a longer period of time. I don't think the difference in money is a lot. All right.
Okay.
Any questions? Any question, guys? Now, for those who don't have the book, I think also if you purchase the loose ends, it will come with the access code, and it's not very expensive. It's, I don't know, like 112 or so. I mean, relatively not expensive. Any other questions? Can you guys hear me? Yeah, any other questions? All right, bye-bye, guys. I'll see you tomorrow then. And I have office hours now, so you guys can meet me there.
Have a good day.
Goodbye.
Bye.